Welcome to the first unit of Math 121. In this unit, we're going to review the common functions that we use in calculus and how we can transform those functions to obtain new functions that have different properties. As a quick concept check, we have the graphs here of four different functions: e to the x, ln of x squared, and x to the 1/2. Just as a getting started exercise, think of which graph represents the x to the 1/2 graph among the four here. We'll pause for a second, and then we'll check that out. All right, x to the 1/2 is also better known as the square root of x function. And one property of the square root of x function is that it goes through 0, 0, because the square root of 0 is 0. And it's also the inverse of the x squared function, which is a parabola. And that means here we have b being our x squared function, the classic parabola. The root x function is that same function reflected in the line y equals x. When we see these two graphs related to each other, we can see that they're reflections of one another, and that indicates that graph C is the function for the root of x, or x to the 1/2. Similarly, we can look at A, and it is growing just like a parabola. So these have different rates of growth. We would not call them both exponential growth, which is often a phrase you hear. The A graph does grow exponentially because it has an e with the x in the power. The red line graph B is the graph of a parabola, which simply grows at a quadratic rate. Last but not least, we have the graph of ln of x for D here, and that graph has the property, among others, that the ln of 1 is equal to 0, and that comes from the fact that the exponential function, graph A here, and the graph D are inverses, so they are the same graph reflected in the y equals x line. If that felt a little shaky, I would recommend going back and just taking a look at common graphs that you've used in the past and just refamiliarize yourself with them and their basic shapes. On this page, we'll comment on some of the structures we just saw graphically. In particular, when we look at inverse partners, such as x squared and square root of x, or e to the x and ln of x, those have the symmetry or the reflection across the y equals x line. If you know the graph of one function and then you're asked for the graph of the inverse, you can construct it using that approach. Graphs of exponentials like e to the x or 2 to the x or 10 to the x. For now, we'll leave out leading coefficients. So these basic building blocks, these have some nice properties to them. They are always positive. There is no way to plug in x and get a negative number out of any of these functions. And they all go through the point 0, 1. If you plug x equals 0 into any of these functions, they all equal each other and give you the value 1 back. Next up, logarithms. These curves are the inverses of exponentials. So again, we can use the symmetry from the y equals x line as a property, and these look like ln of x, or log base 2 of x, or log base 10 of x. Those would be the inverses, say, of the three functions here, though we could also use different bases like 5, pi, whatever you like. Some of the basic properties of logarithms is that they grow very slowly for large x. And what does that mean? Well, graphically, those functions are going to start and they're all bent over, concave down, and they keep growing, they keep going up and up forever, but it's at a slower and slower rate or at a lower and lower slope, as we'll see when we get to derivatives. These graphs are also undefined for x values that are less than 0. And that comes directly from the exponentials being always positive, meaning when we go the other way around, here it's y values are always positive, here we have to have x values always positive. And in fact, we can't even have it equal to 0 there. There's no log of a 0 value. Powers of x, this can include fractional powers as well, so roots, or x to the 10, or even x to the -3. For these functions, if we have a positive exponent, then we go through the point 0, 0. If you plug x equals 0 into any one of these functions, you're going to get a 0 value back. That doesn't work for the negative exponents. For these ones, these are undefined at x equals 0. We start getting asymptotes if you have negative powers of x as your function building block. Now that's only the tip of the iceberg. What other kinds of functions are we going to deal with in this course specifically? We're going to have trig functions, our favorite, sine, cosine, tangent, etc., cosecant. Those will all be reviewed again, but a bit later. There's a lot of ancillary information or ideas around trig functions that we'll want to bring in at the same time, so we'll postpone that a little bit. We also have the class of inverse trig functions, and those are called arcsine, or some students have it introduced as sine to the power -1, and again that we'll get into a little bit later as well. If you haven't seen it before, we will introduce it in a bit more detail. Aside from those, we can also combine our power functions into polynomials. So 5x squared plus 3x plus 2, that would be a combination of powers of x, combining with constants, addition, subtraction, and that gives us a whole other family to work with. Going even further, we can look at rational functions, and that's where we have a polynomial divided by a polynomial function in a ratio. That's where that rational term comes from. It comes from the word ratio. We also have, what else? We have absolute values, and we can combine our functions in different ways again by looking at piecewise functions. And those functions are simply written out in different intervals. So if we say for x greater than 0, we're going to use the quadratic function x squared, but for x less than or equal to 0, we're going to use the absolute value function. That's a totally reasonable way to combine these two functions, but we combine them on different intervals of our x. So here we'd have the absolute value function, and on this side we would have the x squared. This is a typical notation we will use in the course. Giving examples of each member, we've already done a bit of this, but let's go a bit further. So again, trig functions would be sine and cosine. Inverse trig, those would be arcsine, that'll be the typical name we will use. Arccos and arctan will be the big three that we will explore a little later in the course. Rational functions would be something like x squared plus 1 over 3x minus 2. The absolute value function is worth exploring in a little more detail. That would be a function equaling the absolute value of x. That has a nice tie into the piecewise, because these symbols are hard to manipulate. A lot of the ideas in calculus about derivatives we don't have rules for how that applies to absolute values. So another way to write this is as a piecewise function. And because the absolute value works differently when x is positive or x is negative, this is a perfectly reasonable way to start writing out this absolute value and what it means. Working through this in words a bit, if our x value is positive, then there is no change. If you have absolute value of 2, you get 2. Absolute value of 5, you get 5. And what that means is, if we have an x value that's positive, we just get x back. Now what happens on the other side? If x is negative, then imagining minus 2, we want to get 2 back. The challenge here is to get away from the idea of just remove the negative sign. There's no mathematical formula way to do that except for the absolute value, and we're trying to use something different. If you think about this for a moment, if you think if our x is negative, then if we want to make it positive, one way to achieve that is to put another negative in front of it. So we would have a negative value times a negative x, and that whole thing is going to be the positive version of x, or the absolute value of x. Might seem a bit counterintuitive initially, but by adding a second negative, we're going to make things positive again. This formula for the absolute value is going to come back a couple times, especially in the next few weeks. when we start looking at continuity and differentiation. As we already mentioned, this is also a way to write a function out in piecewise notation, just as we saw on the last page. Now that we have these building blocks, our next step is to see how we might be able to transform them to make them even more flexible and useful for modeling.